Our first strategy in solving trig equations involves factoring. Just so you know, this is actually the fourth time I've tried to film this little video. First time I flubbed out. Second and third time, the program quit right at the end. And I just want you to know that it was perfect. It was probably the best educational video you could have ever witnessed. Everything from here on out is going to be subpar. Okay, so let's try to slog our way through this one. Everything that's on this slide, these are the things that you can do, not just for factoring trig equations, but for any kind of polynomial equation. You want to get everything on one side and make it equal to 0. You want to see if you can factor out a greatest common factor, a GCF, if they have something in common. If it's quadratic, you can try to reverse FOIL, what we usually just call factor. If you're so adventurous, maybe completing the square. If it doesn't factor, maybe you have to use the quadratic formula. If there's 4 terms, maybe you want to do factoring by grouping, where you group up the first set, group up the second set, and see if there's anything you can pull out. If it's of higher order, you have to use the rational zero test, where you find the possible factors by looking at factors of the leading coefficient, factors of the constant term, and then test those things out using synthetic division. It's real fun. We'll take a look at that in just a little bit. First equation, x cubed equals x. I want to subtract over the x, make it equal to 0, and I can see that it has a greatest common factor of x. So I want to factor it out. X times x squared minus 1 equals 0. Now I could factor this term right here as a difference of 2 squares, but since I already have it as a product, I can just set both of those equal to 0 by the zero product property. So the first one, x equals 0, done. Or the second one, x squared minus 1 equals 0, add the 1 over, take the square root, so x is equal to plus or minus the square root of 1, which is 1. Remember, every time I take the square root and solve an equation, I should have 2 answers, positive 1 and a negative 1. And notice I could have gotten both of those answers if I had factored that as the difference of 2 squares, x plus 1 and x minus 1. Still would have given me those. Excellent. Okay, on the trig side of things, this time subtract over this cosine to that side. So I have cosine cubed x minus cosine x equals 0. There's a common factor of cosine, so I'm going to factor it out. What's left behind is cosine squared x minus 1. And now, just go ahead and set both of those factors equal to 0. First one, cosine x equals 0, root. Second one, cosine squared x minus 1 equals 0. So on the left-hand side here, draw ourselves a unit circle, egg-shaped, of course. Try to figure out where is cosine equal to 0. Well, I think cosine equal to 0 right here at pi over 2. Well, it's also equal to 0 at 3 pi over 2. And then back up all the way around, and notice that I'm just taking, I'm going around by pi this time. So x is equal to pi over 2 plus n pi. That takes care of all of those. Sometimes the quadrant angles, like the 0, 90, 180, 270, those things are special. They don't always have to go by just the period. Okay, over here on the right hand side, cosine squared x equals 1. When I add the 1, take the square root. Cosine x equals plus or minus square root of 1, which is 1. Remember, this is really 2 equations. It's cosine x equals 1 and cosine x equals negative 1. We have to solve both of them. Draw another unit circle. This one has a little tail on it. Okay, where's cosine equal to positive 1? We're going to do this top equation first. It's equal to positive 1 here at 0, and then back around to 2 pi, and then 4 pi, and then whatever. So x is equal to 0 plus 2n pi. You don't have to have the 0 there, it's optional. Okay, where is cosine equal to negative 1? It's over here at pi. I can add 2 pi to that and get 3 pi. So x is equal to pi plus 2n pi. Now, just like I did on this other side, I can just go from 0, add pi, get pi, add another pi, get 2 pi. So really this is just x equals n pi, multiples of pi. The end.